Power and Propulsion Laboratory at the University of Maryland under the mentorship of Dr. Raymond Cedric. His project was funded by the National Aeronautics and Space Administration to develop parts for a rover to be sent to the Jupiter moon of Europa to discover life-habitable conditions. Specifically, Khalil worked on and tested the ice pick, an end effector to be put on the legs of the rover. Please give a warm welcome to Khalil.
Oh, yeah.
Good afternoon, everyone. So I'd like to give a thank you to Mabruk for that really swell presiding speech. As Mabruk stated, I worked at UMD in the Space Power and Propulsion Laboratory, and the title of my project is the development of the icy cryo environment penetrating ice claw for rover travel on the Jupiter moon of Europa. So first, I'd like to give you a little bit of background about my project. So the Jupiter moon of Europa is completely covered in ice. And what's special about this moon is that scientists hypothesize that there's water underneath the ice in subsurface oceans. And for this reason, scientists are looking to send rovers to Europa. But the current designs of the rovers that have gone to Mars will not suffice for this new environment because the Martian terrain is very sandy and made of dirt, whereas Europa, as I said, is made completely of ice. So for this project, we must make a novel generation of rovers, something new and something creative that will be able to traverse the slippery, icy terrain of Europa. But first, I'd like to get to something that many people are wondering about, the outer space aliens. So the thing about Europa is that there's subsurface oceans are ideal for extraterrestrial life, meaning that they contain the elements needed for life to exist, such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfate. So the scientists hypothesize that some parts of the Europa subsurface oceans mimic hydrothermal vents that can be found here on Earth. And as some of you may know, hydrothermal vents are where some scientists hypothesize life began at first. So if there are hydrothermal vents in Europa, then there's a high chance that there's life on Europa. And because of this reason specifically, the scientific community has put a lot of funding into creating a rover that can travel to Europa, especially companies like NASA, for example. So the specific objective of my project was to revolutionize the transportation used by these rovers. So right now, current designs usually use treads or wheels, but for the icy terrain of Europa, we must use a legged vehicle. And specifically, my project deals with the claws on the leg, which will be able to provide boreholes into the ice that the rover can travel upon. So the sublimation rod, which is pictured here, is basically the nail on the claw, or what the rover will use to dig into the ice to create a grip for itself as it travels along the terrain. So continuing the objectives, my project specifically looks at the heat needed to create a borehole. So what that means is that there's ice everywhere. So instead of just mechanically driving the claw into the ice, which would compromise the surrounding environment, we would like to heat up our claw so that it melts a hole into the ice. And for this, we need to optimize the energy usage, which means we need the most efficient design possible. So we determined the optimal tip shape of the claw, the optimal physical composition, the optimal starting temperature that the claw would be when it first creates a borehole, and then the heat inputted into the claw as it continues to melt a borehole. So how do we do this? So the first step was using the SolidWorks program to create a thermal simulation. And what this did was map a temperature gradient for the claw, which showed where the heat would travel throughout the process so we could track the energy usage. Next was stress testing, which was important for the physical composition of the claw, because we needed to make sure we had a material that would not compromise or break under the stress. Next, we went into live testing using dry ice models in an 80-20 frame, which are basically metal rods that we set up to use to mimic the process of the sublimation rod entering ice. We used a power supply to heat up the rover claw, and then we use a thermocouple to actually track where the heat is going during each trial through physical means. And lastly, there was lots of hypothesizing, as this is the early stage of a 4-year project. So right now we're just looking into the prototypes, or we're looking into how we're going to make the prototypes, which means that we had to do a lot of guesswork and we didn't do many statistical analyses of the data we found. So the first graph I'd like to show is the heat input effect on efficiency. So on the x-axis, we have the trial number, and the y-axis is the efficiency calculated. And the way we calculate efficiency for this project was determining, using Ohm's law, the amount of energy that it would actually take to melt a borehole, and then as the numerator of the efficiency equation, and then or expression, and then under that we use the actual energy that it took for our trial, which means if we took the exact amount of energy calculated to create the borehole, then it would be efficiency of 1. But the more energy it took that was wasted, the lower the efficiency. So at the top line, we have the 18 voltage input into the claw, the results from that. And then at the bottom line, we have the 24 voltage inputs into the claw. And as you can see, the 18 volt input usually had a higher efficiency for each trial. Next, we have the starting temperature efficiency effect on the efficiency. The starting temperatures at the top here are the 80 degrees Celsius starting temperatures, which are the triangles, but maybe hard to see. And then we have the 40 degree starting temperatures as the red circles, and at the bottom there are the 25 degree starting temperatures. And as you can see, the efficiency increases along the y-axis, so that the 80 degrees Celsius starting temperatures were usually the most efficient trials. Our third design implementation we're trying to use is the tip shape, which here at the top we have the conical tip shape, which means it was pointed, and on the bottom we have the inverse conical tip shape, which means it was inverted, and it kind of acted like a test trial or a control to see how the shape of our nail would actually affect it. And here the conical tip shape has a greater efficiency, and the sporadic values of the inverse conical tip shape show that it was an efficient trial or efficient design. So finally we have our analyses of what our data concluded. So our tip shape we wanted to be conical because it created a cleaner borehole, which means that the point allowed the rover to sublimate downwards more easily because it was pointed, so it didn't shake or move around a lot. And this created a smaller borehole because instead of the radius being large and wasting energy to sublimate the larger radius, it had a smaller borehole, and this in fact made the energy usage more optimal. And lastly, we hypothesized that there was a carbon dioxide buildup in the inverse conical tip shape, which was the cause for the sporadic values as seen here. The starting temperature we agreed was most optimal was the high starting temperature at 80 degrees. For the 80 degree starting temperature, as soon as the sublimator touches the ice, it's already heated, so it in turn creates a smaller borehole, and as I explained, this makes the energy usage more optimal, and it doesn't allow energy to escape from creating a larger borehole and having more ice to sublimate. The heat input we wanted to use was low at 18 volts, because with the 24 volt trials, a lot of the heat escaped onto the sides or up and down and to heat the CO2 gas created. So we wanted the 18 volt trials, or the 18 volts inputted into our claw, because it allowed heat to concentrate downwards to solely sublimate what it needed to be to create a grip. And then lastly, our stress test told us that we need a copper material because it withstood a 50-pound weight, and neither material, the copper nor the dry ice, was compromised in our test. So our conclusion is that the design that will optimize efficiency is a design with a conical tip that's made of copper, heated to 80 degrees before it makes contact with the ice, and then implemented with 18 volts of energy. So our future goals is to develop the rest of the claw, and this is the sort of design we're looking at, like a vending machine claw where the sublimator rods would be at each point, the 3 points here, and it would use it to like crab walk across the terrain. We want to develop the rest of the rover, which is the sensors in the body of the rover. We want to continue into vacuum tests. Here at UMD, there's a lab where they can mimic the no atmosphere conditions of Europa, and we want to do tests there to see what it would be like without an atmosphere for our rover's functionality. And then lastly, we want to continue on to mobility tests to see if the crab walking type method actually works and does not compromise the rover or create problems that are unforeseen to us currently. So I'd like to give a thanks to first and foremost my mentor, who's Dr. Raymond Sedgwick at the University of Maryland. My graduate student, Alan Halperin, he was getting his PhD from the University of Maryland. I'd like to thank NASA for funding my project. I'd like to thank Ms. Aksaria because she's my SRP teacher, and she basically helped me throughout this whole year to make sure that my presentation was what it is, or hopefully it's good, but yeah. I like to thank Miss Bradshaw as well because she helped me get my internship. She was there. I contacted her a lot. Mr. Curran, the head of our house, he helped a lot throughout the past 4 years to make sure that every person in SMAX was ready for this occasion. I like to thank my other teachers, Mr. Kingman, who taught us about geology, especially Mr. Lee, who was our SRP.
Good job, Bishop.
I like to thank. I also like to thank Mr. Lee, who was our SRP teacher last year. He worked really hard to make sure that every student was able to find an internship, and without him, like, none of us would have any of our internships. And then lastly, Dr. Miller, because she was a teacher, but she retired, and basically all the other teachers too. So any questions? I'll start with Kashif.
Since your team was like pretty hypothetical, were you able to, like, in the time that you were there, like actually develop anything or like test any actual materials?
Okay, so Kashif asked if I was able to test any actual materials, because I did state that a lot of the processes in our experiments were they were inconclusive in terms of that we cannot finalize them because we did not do statistical analysis. But I did model and brainstorm designs for the end effector, and a lot of these designs my mentor went on to create like physically using copper material, and these are what he's testing on. So that was one thing that I did create that was very like physical and productive, substantial. Yes, Praneeth.
Do you think NASA will use this like anytime in the future?
I do believe NASA will use this sometime in the future as they want to go to Europa to see if there's life there.
All right.
So yeah. Glenn?
So I know for all of us who did our SRT, there's a transition period needed going from school and what we learned in school and the extracurriculars we do at school into our internship. How do these things prepare for you, and like what period of time? What kind of transitional period do you need going from school to NASA?
So Glenn basically asked me what the transitional period between me going from school to working on here is. And I found there was a sort of learning curve at first, because a lot of times I would try to impress my mentor. I wouldn't ask questions. So he would show me how to use a certain program, and he'd be like, do you know how to use it? Do you get what I'm saying? I would nod along. And he would ask me to do it myself, and I would click one button, and the whole thing would crash. Once I got the learning curve done, it was pretty easy to like assimilate myself into the culture of what everyone I was working with, and that I could learn stuff quickly, and I was able to keep up with them and understand what they were saying. So in terms of that, there wasn't much of a learning curve, but it was there definitely. Justin?
What was your favorite part about the internship?
Bruh.
My favorite part, that's really hard because I like a lot about my internship. I like the work hours mostly because it was a lot of time for us to get what we need to get done completed, and there was it was enough time, and I really enjoyed that. I didn't want to be rushed or feel like I had to come in and then get out immediately. So I think that was.
So what was your least favorite part of the internship?
That's like saying like what's the least favorite part of your cake. Like I love everything. Like I would say probably the least favorite part. Yeah, it could be when it was over, but it probably was doing a lot of the modeling on the computer instead of the physical. Like there was dry ice testing, but a lot of the time spent was on the computer modeling. So if I could spend more time actually physically working on my project, I think that would be a little bit better. Connor?
What was your greatest challenge that you faced? Like not necessarily bad, but like something that you had to like overcome during your internship.
Using the programs, because I guess I'm not really adept at computer science. So typing and making sure I memorize what all the steps to the modeling and the simulations were, which I had to run a lot of for most of my internship. That was probably the hardest part, just trying to memorize everything. Yes, Praneeth.
Like I know a lot of stuff was inconclusive. Like, do you hope to like work on this in the future, maybe at like NASA?
That would be really interesting. When I'm going to college, I hope to do biological engineering because that's one of my passions. But in terms of this, I would be open to returning next year to try to finish the project because it was one of the highlights of my summer, definitely. Jessica.
So did you try any other designs other than the vertical and the cone?
For this test, we use a flat design, but it broke like halfway through, so we stopped using that. But for now, it's just inverted and the conical tip.
Do you know how NASA plans to power something like this to generate heat to be walking on surface of a far out celestial body? Solar panels don't really tend to work out there.
Wait, can you repeat that? Sorry.
Do you know how NASA plans to power something like this running for an extended period of time?
Yeah, so one power supply we were talking about is a piezoelectric motor, which can be is malleable, and when it moves, it creates electricity. So we weren't going to try to take energy from the sun or like through solar panels when we were there, but we have other ways of implementing motors that we're looking into currently. Devin?
So most of your they've been primarily on the model, like you do not have actual. The one, because you listed several characteristics, which one of those were actually based off a physical test versus modeling?
So all of them were a mixture of both. So first we would go in with a physical test to collect our data, then we would implement the data into the model to see where the heat flowed and to track, like simulate basically where all the energy was going. So we combined both to get all of our conclusions. Yes.
What would you say that the courses here at Fools will prompt you through this internship? Like, which specific courses would you rather have taken before you went?
I think all of the courses, especially in the SMACS program, were very helpful. Mr. Kingman, or I guess he left, but his ESS class was very useful in that I had to do a lot of terrain analysis for my project, and he taught us a lot about like how planets work and the surface of planets. The SRP definitely helped. When I was presenting in front of my fellow colleagues, I was able to speak clearly, I would say, and I got a lot of confidence from practicing so much during the SMACS presentations. Beyond that, I think Dr. Stone's physics class was a large part of it because I had to calculate a lot about Ohm's law and power. I had to calculate a lot about Ohm's law and power, and I think that was one of the things that really helped.
What about engineering?
Oh, and engineering, of course. The design process I learned from engineering. Yeah. Yes.
Do like any extracurricular clubs help you?
Can you repeat that? Oh, I didn't hear you. Sorry.
Do any extracurricular clubs help you?
So you asked me if any extracurricular clubs help. I'd say that Invent Team was one of the biggest factors into my, because the way we were in that club.